protocol can be considered as the bridge between an application and a communication link. Protocols function as a common set of rules governing the exchange of data between devices on a network. We can equate protocols to languages such as English, French, or German that are used to exchange thoughts and ideas between two people. There are certain rules associated with the correct use of any language. The same is true of a protocol. The protocol determines such things as the initialization of the data link, meaning the point at which devices agree to exchange data. This is called a logical connection. Many devices have the capability to have more than one logical connection or conversation at a time. The actual conversation is referred to as a communication session. The protocol also determines the services that are supported. For example, reading from or writing to a device, flow control, frame format, synchronization, and error control. In this next section, we will be dealing with details of the Modbus Remote Terminal Unit Protocol. This section is at a technical level intended for system integrators and those interested in in-depth knowledge of GE Multilin's implementation of the Modbus RTU protocol and LAN optimization. There are many existing protocols. In North America, traditionally, Modbus RTU has been the most popular protocol used in industrial power applications, while DNP has generally been the most popular for utility applications. Having said this, the new IEC 61850 protocol is rapidly gaining worldwide acceptance, at least among power utilities. Typically, earlier protocols such as Modbus were based on a master-slave model. With this protocol, there is one master on the LAN and multiple slaves. Each slave is assigned its own slave address. The master can direct a command to a particular slave by using the unique slave address, or the master can send the command to all slaves using the broadcast address 0. When device-to-device data transfer is required, the master would simply read the data from one device and write the data to the second device. It's been found that master-slave protocols such as Modbus work quite well when the maximum required data update is less than half of what the protocol and network are capable of delivering. Within the Modbus specification, there are two serial transmission modes, ASCII and RTU. When using Modbus ASCII, the characters are encoded in the ASCII format, as opposed to the hexadecimal format used with Modbus RTU. GE Multilin relays act as slave devices and only require a subset of the Modbus RTU protocol. Having said this, the supported commands do allow extensive monitoring, programming, and control functionality. The physical layer of the Modbus RTU protocol can be any of a variety of hardware interfaces supported within GE Multilin's family of protective relays, including RS-232, RS-485, 10100 base T, and 10100 base F Ethernet. Data flow is half-duplex in all configurations. The master transmits a command, and the slave then responds. When connected to RS-232 or RS-485 networks, only the physical, data link, and application layers are used. Modbus communication takes place in packets, which are groups of asynchronously transmitted bytes of data arranged in a specific order. These packets are referred to as data frames. The data link layer is responsible for ensuring that the data is framed correctly. The master transmits a packet to the slave, and the slave responds with a packet. The end of both data packets is marked by dead time on the communications line. When troubleshooting or optimizing a Modbus LAN, it is very useful to understand how commands and data are transmitted. When using the Modbus protocol on GE Multilin relays, it's important to note that slave addresses can be assigned to all ports except for the front RS-232 port. This means that the front RS-232 port cannot be connected on a network to a Modbus master. The primary purpose of the front RS-232 port is for relay configuration and troubleshooting. A fixed front port configuration reduces the time and effort required to establish communications to the relay. The front RS-232 port uses a reduced set of the Modbus protocol known as point-to-point Modbus. When using point-to-point Modbus, the slave ignores the slave address portion of the Modbus message originating from the master, assuming that it is the only device networked to the master. Upon receiving a valid Modbus command, regardless of the slave address, the slave will respond to the command, making it impossible to share a network with other Modbus slaves. Within the Modbus RTU protocol, each character is transmitted in an asynchronous format consisting of 1 start bit, 8 data bits, 1 stop bit, and possibly 1 parity bit. This produces a 10 or 11-bit character. This can be an important point for transmission through modems at high bit rates, because an 11-bit character may not be supported by many modems at baud rates greater than 300 bits per second. Baud rates from 300 to 19,200 bits per second are available on most GE multilin relays, with even higher baud rates available with the universal relay. Note that the front RS-232 ports on some relays have fixed configurations. Available parity options are even, odd, and no parity. Messages transmitted over Modbus are comprised of one or more data packets. Each data packet is made up of multiple characters. These characters are separated into different groupings, with each group performing a specific function during communication. The arrangement and functions of these groups of characters is known as framing. Let's look at the framing of a Modbus RTU command data packet in greater detail. During successful transmission, each data packet will begin with a silent interval of at least 3.5 character times. This delay can be calculated by dividing the bits per character by the baud rate. The result is then multiplied by 3.5. The silent interval is then followed by the device address, the function code, the data, the CRC, and then another silent interval. Sometimes errors can occur during the transmission of a message. One type of error that can occur is a silent interval created during transmission of more than 1.5 character times. To illustrate the error-checking functions within Modbus, we will now look at an example transmission of a message. The first data packet of our message is transmitted without error. Once the slave receives this data packet, it uses an error-checking mechanism which is known as the 16-bit cyclic redundancy checksum to ensure the data packet was transmitted correctly. This mechanism is encapsulated in each data packet and is calculated by the master and checked by the receiver. We will discuss the operation of this mechanism later in this section. After this error checking, the slave sends an acknowledge signal to the master. During transmission of the second data packet, an error occurs, and there is a silent interval created of 2 character times. When the slave receives this silent interval, it will discard the corrupted second data packet and not send any acknowledge signal. The master will then resend the second data packet because it received no response. The slave will then error check this data packet and send back an acknowledge signal. The third and final data packet is then transmitted error-free, and the slave sends back an acknowledge signal. This concludes the successful transmission of the message from the master to the slave. Slaves monitor the network continuously. When the master transmits a data packet, the address field corresponds to the slave device that the data packet is intended for. This means that each slave device on the LAN must have a unique address. When each slave receives a data packet, they decode the first field to see if the address of the data packet matches their slave address. The address field of the data packet is 8 bits in length for RTU mode. The range of valid slave device addresses is from 1 to 247 in the decimal system. Only the slave whose address matches the address field will respond. When the slave sends its response, it places its own address in the address field of the response data packet to let the master know which slave is responding. When the master sends a broadcast command, the address field will contain 0. All slaves will recognize this as a broadcast command and will take the command action. None of the slaves will send a response to the master. Within GE multilin relays, the broadcast address is only recognized when the second field, which is the function code field, contains function code 05 hexadecimal, or hex. For GE multilin relays, a packet with a broadcast address of 0 and a function code other than 05 hex will be considered invalid and will be ignored. The function code field of a message frame contains an 8-bit code that tells the slave what action to perform. For Modbus RTU, valid codes range from 1 to 255 decimal. However, GE multilin relays can provide the necessary functionality supporting only function codes 3, 4, 5, 6, and 16. If the slave device accepts the request without an error, it returns the same code in its response data packet. If an exception occurs, the bit pattern of the function code field will be the same as the original function code bit pattern with the exception of the most significant bit. This bit would be set to a logic 1 state. For an exception response, in addition to the modification of the function code, the slave would place a unique code into the data field of the response message. This additional information would tell the master what kind of error occurred or the reason for the exception. The master's application program has the responsibility of handling exception responses. The content of the data field will vary both in the number of bytes and the content, depending on the function code. The content may be actual values, settings, or addresses. CRC16 stands for 16-bit cyclic redundancy checksum. The RTU version of Modbus includes a 16-bit cyclic redundancy check with every packet, which is an industry standard method used for error detection. If a Modbus slave device receives a packet in which an error is indicated by the CRC, the slave device will not act upon or respond to the packet, thus preventing any erroneous operations. As stated earlier, a packet is terminated when no data is received for a period of 3.5 byte transmission times, which is about 2 milliseconds at 19,200 bits per second. Once the dead time has expired without a new byte transmission, all slaves start listening for a new packet from the master with the exception of the slave that had just received the request. This slave builds and then transmits the appropriate response. Modbus officially defines function codes 1 through 127, although only a subset is generally needed. GE multilin relays support the functions listed in this table. Within the GE multilin relays implementation of the Modbus RTU protocol, either function code 03 or 04 can be used to retrieve settings or actual values. It is common to document the organization of a microprocessor's memory in the form of what is referred to as a memory map. The memory map will show where data is stored in the microprocessor's memory and will take on the form of a table showing the memory address, usually in hexadecimal, the content of the memory location, and the format of how the data is stored. Here's an example of a portion of the GE multilin F60 Universal Relays memory map. From this map, we can see the data contained within different memory addresses, the range of the data count, the units that the data is in, scaling information, and the default value if applicable. As an example, let's take a look at memory location 4050 hex. This location contains what is called the flash message setting. The permitted range of this setting is from 0.5 to 10 seconds. The value can be modified in units of 0.1 seconds and is stored as a 16-bit unsigned integer. A data register is a memory location within the CPU dedicated to a specific actual value or setting. Data registers are always 16-bit or 2-byte values transmitted with the high-order byte first. The maximum number of consecutive registers that can be read in a single packet is 125. Here we can see the format and content of the command data packets transmitted by the master to slave number 1 requesting the content of register 4050. After an idle time of 3.5 characters, the master transmits the command with the following packet sequence and content in hexadecimal. The slave address is 1, the function code is 4, the data starting address high byte is 40, the data starting address lower byte is 50, the number of registers high byte is 00, the number of registers low byte is 01, the CRC low byte is 24, and the CRC high byte is 1B. After this packet sequence is transmitted, the master will be idle for 3.5 character times. With the flash message set to a value of 05 hex, we would expect the following response in hexadecimal from slave number 1, followed by an idle time of 3.5 characters. The slave address is 1, the function code is 4, the byte count is 2, the data number 1 high byte is 00, the data number 1 low byte is 05, the CRC low byte is 79, and the CRC high byte is 33. After this packet sequence is transmitted, the master will be idle for 3.5 character times. We can see that the flash message time of 0.5 seconds was transmitted back to the master. The first objective of this lab is to familiarize the student with the Modbus RTU protocol by observing the transmission of a data packet between a Modbus master and a slave. We'll be using a demonstration Modbus master and protocol analyzer application called ICOM-104. The second objective of this lab is to become familiar with the Modbus user map feature of the GE multilin relays. First, we connect the computer to the relay using the serial cable and configure the flash message time of the relay's display to 0.5 seconds. We will then configure the Modbus Master and Protocol Analyzer software. First, we select the COM port that has been configured on the computer to be the serial port. Handshaking. For multilin relays, we will select 2 for DTR. Then we select the default baud rate of the GE multilin relay's front port. For the UR relay, this is 19,200 bits per second, and so 6 will be entered. For run mode, we select 2 for 1 shot to configure the protocol analyzer to transmit one read command, display it, and the slave's response each time a key is pressed. We select 1 to ensure that the protocol analyzer will continue if it receives an error from the slave. We'll select 2 to enable sound on error. For the display mode, 1 is selected for hexadecimal display because the protocol is Modbus RTU, which transmits characters in hexadecimal. For the protocol type, we select 1 for RTU. Since we're using the relay's front serial port, which uses the point-to-point Modbus RTU protocol, the slave address doesn't really matter. We will select 1. The starting address is where we enter the starting memory address of the slave memory area we want the software to read. With reference to the Universal Relay F60 memory map, we can see that the flash message time starts at location 4050 hex, and so this starting address is entered. From the memory map, we can see that the data stored at location 4050, which is the flash message time, has the format of unsigned 16-bit integer, which is 2 bytes in length. We will therefore enter 2 for the number of bytes. Once the byte count has been entered, we get the following display. The request line displays in hexadecimal the packet sequence and content of the command sent from the software to the slave relay. The response line displays the packet sequence and content of the slave relay's response in hexadecimal. From this exercise, we can see that the Modbus RTU command and response is as predicted by the lecture. If the setting flash message time is changed via the keypad to 0.6 seconds and any key on the computer keyboard is pressed, the read will be performed again, and the content of the response shows that the content of location 4050 is 06 hex. If an error occurs, we'll get an error message and a beep from the computer. Under such a condition, the baud rate, serial cable, and serial communications port assignment in the computer should be checked, and once the fault is corrected, repeat the previous steps. If all the data that is required by the master is located in consecutive memory locations within the slave, it can be read and updated within the master's memory on a periodic basis using a single read command. This, however, is rarely the situation. Normally, the required information is located in several different areas of the slave's memory. To update all the data requires multiple read commands, increasing the required time for the master to get a complete update. To reduce this time, all GE multilin relays have a Modbus user map. Once this map is configured, all information required by the master is stored in the consecutive memory locations of the Modbus user map, which then enables the master to retrieve all desired information with one read command. As an example of how to configure the F60 user memory map, let's say that a master were interested in the flash message time located in memory location 4050 hex and the phase CT primary located in memory location 4480 hex. Both these values are stored in 16-bit unsigned integer. The Modbus user map starts at memory location 1200 hex. They will both be stored in the Modbus user map locations 1200 and 1201 respectively. Using the EnterVista setup software, open the Product Setup menu and then the Modbus user map. Enter 4050 hex in the first parameter field and 4480 hex into the second. To test, we configure the ICOM-104 software for a starting memory location of 1200 hex and a length of 4 bytes. From the command packet sequence, we can see that the ICOM-104 master is requesting 4 bytes from the start of the Modbus user map address 1200 hex. The response from the slave contains the values of the settings for both the flash message time, 0.5 seconds, and the phase CT primary of 64 hex or 100 decimal. This completes our lab. The D485 and P485 converters work in a similar fashion. The D485 is a Modbus to DeviceNet converter, allowing data exchange between any multilin relay or meter supporting the Modbus protocol and a DeviceNet network. while the P485 performs the same functions between any multilin relay or meter supporting the Modbus protocol and a Profibus DP network. Let's look at the operation of these converters. Data from either the DeviceNet or Profibus network is stored within the converter's internal memory buffer for transmission to the relays and meters on the Modbus LAN. The converter then acts as a Modbus master and writes this data to the Modbus slave or slaves on the Modbus LAN. The converter also reads data from the slaves and stores this information in its memory such that it can be read by the DeviceNet or Profibus masters. In either case, the buffer stores three different types of data: input, output, and general data. Input data is sent to either the DeviceNet or Profibus master from the Modbus LAN, while output data is sent to the Modbus LAN. General data cannot be accessed from the Profibus or DeviceNet LAN and is used for transfers between slaves on the Modbus network or as a general scratchpad for data. Either converter can handle up to 1024 bytes of general data. Note that the EnerVista P485 D485 setup software program is used to configure both converters.